Hi friends, today our topic is dwdm. Fiber is a thin strand of glass or plastic that serves as the dwdm transmission medium. Optical fiber is a dwdm transmission medium. For single mode, the loss is 0.275 dB per kilometer for 1550 nanometer window, and for 1309 nanometer, 0.5 dB per kilometer is the loss. Multiplexing is the process of combining two or more signals together based on space, time, or wavelengths. Different signals with specific wavelengths are multiplexed into a fiber for transmission. Earlier, HDS technology was having very less capacity, so there came DWDM technology. DWDM is a transmission technology which is we can transmit multiplex or demultiplex different wavelength on a single fiber by which we can utilize maximum bandwidth of fiber. Via fiber. DWDM combines multiple optical signals so they can amplified on a group and transmitted over a single fiber to increase capacity. Here are multiple bands. First there is O band, multiple windows. O band, original 1260 to 1360 nanometer. E band, extended 1360 to 1460 nanometer. S band, short wavelength band 1460 to 1530 nanometer. C band, conventional or RBM window 1530 to 1565 nanometer. L band, long wavelengths 1565 to 1625 nanometer. U band, ultra long wavelengths 1625 to 1675 nanometer. O band 1260 to 1360 nanometer. E band, extended 1360 to 1460 nanometer. S band, short wavelength 1460 to 1530 nanometer. C band, conventional or RBM window 1530 to 1565 nanometer. L band, long wavelength 1565 to 1625 nanometer. U band, ultra long wavelength 1625 to 1775 nanometer. O and E around 1300 nanometer have much more losses. This region has zero dispersion, but this region has zero dispersion. When we consider middle windows, S and C are most widely used. But for DWDM, we use C and L bands. C and L bands are most widely used for DWDM. It does have more some dispersion, but with minimum loss of 0.275 dB per kilometer. We use dispersion capacitor to compensate dispersion for C and L bands. Channel spacing is minimum for minimum frequency separation between two different multiplex signals. What is channel spacing? Channel spacing is minimum frequency separation between two different multiplex signals. In 1980s, there was wide band WDM 1310 nanometer and 1550 nanometer, two channels. Early 1990, 2 to 8 channels in 1550 nanometer. Second generation, that was second generation DWDM. Second generation WDM channel spacing was 3.2 nanometer. In mid 1990s, 16 to 40 channels in 1550 nanometer window, that is DWDM. Channel spacing was 5.8 to 1.6 nanometer. In late 1990, in mid 1990s, 16 to 40 channels in 1550 nanometer window DWDM. Channel spacing was 0.8 to 1.6 nanometer. In late 1990s, 64 to 160 channels in 1550 nanometer. That is next generation DWDM. Channel spacing is 0.2 to 0.4 nanometer. A basic DWDM system contains below main components. Some main components. What are the components? First, OTM, optical terminal multiplexer site. Second is OLA, optical line amplifier, that is repeater site actually. Third is optical intermediate optical terminal, where we pass through channels, that is also called dual terminal. Next is a demultiplexer site, just like OTM actually does both things, multiplexing and demultiplexing. Next final is OSC signal. This is for remote site management. OSC signal carries management signal, DCC signals, and some engineering information also. What is the importance? DWDM is a transmission technology by which we can transmit multiplex, demultiplex different movements on a single fiber, by which we can utilize maximum bandwidth via fiber. O band 1260 to 1360 nanometer, E band 1360 to 1460 nanometer, S band 1460 to 1530 nanometer, C band conventional or Arabian window. This is 1530 to 1565 nanometer, L band long wavelengths 1565 to 1625 nanometer, U band ultra long wavelengths 1625 to 1675 nanometer. Channel spacing is minimum frequency separation between two different multiplex signals. Thank you.